Hello. How's everyone doing? Um, so I'm going to be continuing learning C++ again. Last stream, wait, let me just change the full screen. So, oops. Okay, so last stream, I learned about std array. Why isn't this opening? Yeah, I did std. Hold on, what's happening? Okay, I learned about std array and I did till 17.6. This stream, I'll try to finish all of these. And yeah, let's start with introduction to C style arrays. Now that we have covered vector and array, we will complete our coverage of arrays by covering the last array type, C style array. As mentioned in lesson 16.1, C style arrays were inherited from the C language and are built into the core language of C++. This means we don't need to include a header file to use them. Because they are the only array type natively supported by the language, the standard library array container types are typically implemented using C-style array. So declaring a C-style array, we use square brackets to tell the compiler to declare that a declared object is a C-style array. So testScore 30 defines a C-style array named testScores that contains 30 value initialized int elements, no include required. Inside these square brackets, we can optionally provide the length of the array, which is an integral type of std size t that tells the compiler how many elements are in the array. The following definition creates a C-style array variable named testScores. The length of a C-style array must be at least 1. The compiler will error if the array length is 0, negative, or a non-integral value. Just like array, when declaring a C-style array, the length of the array must be a constant expression. Okay. So subscripting a C-style array, just like array, C-style arrays can be indexed using a subscript operator. Array 5, and then we are accessing the first element or the second element. Okay. Unlike the standard library container classes, which use unsigned indices of type size t, only the index of a C-style array can be a value of any integral type or an unscoped enumeration. This means that C-style arrays are not subject to all of the sign conversion indexing issues that a standard library container classes have. So your constant integer array 98765, and then okay to use signed index, and it's okay to use unsigned index. The subscript operator does not do any bound checking, and passing in an outer bound index will result in undefined behavior. Aggregate initialization of C-style arrays. Just like std arrays, C-style arrays are aggregates, which means they can be initialized using aggregate initialization. As a quick recap, aggregate initialization allows us to directly initialize the member of aggregates. To do this, we provide an initializer list, which is placed in closed list of comma-separated values. So Fibonacci is 6. We have copy list initialization with 0, 1, 1, 2, 3, 5. And then list initialization using brace list. This is preferred. If you do not provide an initializer for a C-style array, the elements will be default initialized. In most cases, this will result in elements being left uninitialized. Because we generally want our elements to be initialized, C-style arrays should be value initialized using empty braces when defined with no initializers. If more initializers are provided in an initializer list than the defined array length, the compiler will error If fewer initializers are provided in an initializer list than the defined array length, the remaining elements without initializers are value initialized. So over here, too many initializers, and then 2, 3 are value initialized. One downside of using C-style array is that elements type must be explicitly specified. CTAT doesn't work because C-style arrays aren't class templates, and using auto to try to deduce the element type of an array from the list of initializers doesn't work either. So auto doesn't work, CTAT doesn't work. There's a subtle redundancy in the following array definition. See it? So const integer prime 5, prime has length 5. You're explicitly telling the compiler that the array has length 5, and then we are initializing it with 5 elements. When we initialize a C-style array with an initializer list, we can omit the length and let the compiler deduce the length of the array from the initializers. This only works when initializers are explicitly provided for all array members. When using an initializer list to initialize all elements of a C-style array, it's preferable to omit the length and let the compiler calculate the length of the array. That way, if initializers are added or removed, the length of the array will automatically adjust, and we are not at risk for a mismatch between the defined array length and the number of initializers provided. Before omitting the length of a C-style array when explicitly initializing every array element with a value. Just like std arrays, C-style arrays can be const or const expression just like other const variables. Const arrays must be initialized and the value of elements cannot be changed afterwards. Okay, so this is a constant, and this will cause a compile error because the values cannot change. In previous lessons, we used size of operator to get the size of an object or type in bytes. Applied to a C-style array, size of returns the number of bytes used by the entire array. Assuming 4 bytes, the above program prints 20. The prime array contains 5 integer elements that are 4 bytes each, so 5 times 4 is 20. Note that there is no overhead here, and a C-style array object contains its element and nothing more. Length 5, 1, 2, 3, 4, 5. What about the terminating character, the /0? That doesn't count, right? But it does take up like a few extra bits, right? In C++ 17, we can use std size, which returns the array length as an unsigned integral value. In C++ 20, we can also use ssize, which returns the array length as a signed integral value. Getting the length of a C-style array. Hold on. Prior to C++ 20, there was no standard library function to get the length of a C-style array. If you are using C++ 11 or C++ 14, you can use this function instead. So template t, size t, n, you have length, return n. So length array, how are they doing this? What is no except? I forgot this. Constant expression, size t. So it's a constant expression function. It returns size t and length, and the input is a const array reference of size n. Yeah, I think I understand. This uses a function template that takes a C-style array by reference and then returns a non-type template parameter representing the array's length. In a much older code basis, you may see the length of a C-style array determined by dividing the size of the entire array by the size of the array element. Uh, okay. This formula can fail quite easily, leaving the program unexpectedly broken. C++17 size and length function template shown above will both cause compilation error in this case, so they're safe to use. They're saying that this formula is not good enough. C-style arrays don't support assignment. Perhaps surprisingly, C++ arrays don't support assignment. Assignment to individual elements is fine, so array assignments are not valid. Technically, this doesn't work because assignment requires the left operand to be modifiable L value. And C-style arrays are not considered modifiable L values. If you need to assign a new list of values to a C to n, why do they use an? To a C-style array, it's best to use a vector instead. Alternatively, you can assign new values to C-style array element by element or use copy to copy the existing C-style array. So std copy, std begin source, std end source, std begin array. I think begin and end what do these output? Do these output pointers? Convert the following array definition into an equivalent constant expression C-style array definition. Constant expression array and then constant, the answer is constant expression int a3 and then default initialized or value initialized. What three things are wrong with the following program? Length 5. I think it has to be a constant expression length. Std array length. I think it should be length -1. Otherwise, you're doing undefined behavior here. And array 0 is 4. Oh, it's a constant, so you cannot reassign. When defining an array, the length must be a compile time constant. In the above, length is a non-constant, so the definition is not allowed. Arrays are indexed from 0 to length -1, and then array elements have type constant integer, so it cannot be reassigned. A perfect square is a natural number whose square root is an integer. We can make perfect squares by multiplying a natural number by itself. The first four perfect squares are 0, 1, 4, 9. Use global constant expression C-style array to hold perfect squares 0 and 9 inclusive. Repeatedly ask the user to enter single digit integer or -1 to quit. Print whether the digit the user entered is a perfect square. The output should match the following. So 4 is a perfect square, 5 is a perfect square. Okay, let's see. I need to remove this. This is from the previous stream. So std enter a single digit integer or -1 to quit. User input and then let me think. We can do while is there a way to check if it's an integer? Do we do static cast? Static cast. User input. Is more than -1. It should be these brackets. So this has to be an integer. stdcn user input. For int I is 0, I is less than user input. Wait, hold on. Should be square root. Can I do square root natively? Is there a way to do square root? Hold on, I will just look at the answer because I don't know if C++ has a square root. And whether the use curve was used to hold perfect squares between 0 and 1 inclusive. Single digit integer. Oh, no, wait. Got it wrong. Const expression squares 0, 4, 9 squares 4. What's wrong? What's wrong with this? So while I is in 0, const expression squares length. Now all we need to do is check whether the integer is like one of these. Um, 4 is a perfect number, 5 is not a perfect number. Is perfect num is false if I should do boolean if user input is equal this is perfect num becomes true. Also, you're going to do this multiple times, right? Uh, no, I should do. Actually, never mind. And then if is perfect number, then S is std cout cout user input is a perfect square slash n is not a perfect square, and then we do else. And then we ask this question again. stdcn and then user input. So what did they do? So match square, or they put a separate function here. They're doing input, cn input. Oh, while true, it's an infinite loop which will break if the input is -1. There's a fail here. C++ does not support default int. What is the issue here? So if I put -1, okay, I quit. And then let's do this again. I put 4. 4 is a perfect square. And then 5 is not a perfect square. Hold on. Should be full stop and then new line. Continuing, if I put 9, 10, 10 is not a perfect, then -1. 8. Should we make sure that the user is inputting single digits? There's no checking over here. C style array decay. C style array decay. The designers of the C language had a problem. Consider the following simple program. So void print cout value. When print x is called, the value of argument x5 is copied into the parameter val. Within the body of the function, the value of val is printed to the console. Because x is cheap to copy, there is no problem here. Now consider a similar program which uses 1,000 elements, a C-style integer array instead of a single integer. This program also compiles and prints the expected 5. While the code in this example is similar to the code in the prior example, mechanically it works a bit different than you might expect. That is due to the solution the C designers came up with to solve two major challenges. First, copying its 1,000 element array every time a function is called is expensive. So we want to avoid that, but how? C doesn't have references, so pass by reference to avoid making a copy of function arguments wasn't an option. Wait, does C not have references? I may be misremembering. I thought C had references. Second, we want to be able to write a single function that can accept array arguments of different lengths. Ideally, our print element 0 function in the example above should be callable within the array arguments of array length. Wait, hold on. We can put a pointer in here, right? We can solve this issue by passing in a pointer. We don't want to have to write a different function for every possible array length that we want to use as an argument. But how? C has no syntax to specify any length arrays, nor does it support templates, nor can arrays of one length be converted to arrays of another length. The designers of the C language came up with a clever solution that solves both of these issues. So int array 1,000 doesn't make a copy, print the value of the first element. Define an array with 7 elements, and this will somehow work. First, we need to cover two subtopics. Array to pointer conversion. In most cases, when a C-style array is used in an expression, the array will be implicitly converted to a pointer to the element type, initialized with the address of the first element. Colloquially, this is called array decay or just decay for short. You can see this in the following program. Save int main 97531. A pointer to array. Evaluation causes array to decay. Type deduction should deduce type int pointer. Prints true if the type of pointer is int pointer. Now let's prove that the pointer holds the address of the first element of the array. On the author machines, this prints true and true. There's nothing special about the pointer that an array decays into. It is a normal pointer that holds the address of the first element. Similarly, a const array decays into a pointer to const. In C++, there are a few common cases where a C-style array doesn't decay. When used as an argument of size of or type ID, when typing the address of the array using the address operator, when passed as a member of a class type, when passed by reference. Because C-style arrays decay into pointers in most cases, it's a common fallacy that to believe arrays are pointers. This is not the case. An array object is a sequence of elements, whereas a pointer object just holds an address. This type of information of an array and a decayed array is different. In the example above, the array ARR has type int5, whereas the decayed array has type int pointer. Notably, the array type int5 contains length information, whereas the decayed array pointer type has int pointer. Pointer type int pointer does not. A decade array pointer does not know how long the array it is pointing to is. The term decay indicates the loss of the length type information. Subscripting a C-style array actually applies this operator to the decayed pointer. Because a C-style array decays to a pointer when evaluated, when a C-style array is subscripted, the subscript is actually operating on a decayed array pointer. Const array, and then the subscript decayed array to get element 2, print 5. Oh, I see. We are accessing this and then printing this. We can use the subscript operator directly on a pointer. If that pointer is holding the address of the first element, the result will be identical. So array, we have pointer. And then if you're using the pointer, we get an identical output. Let's take a deeper look at how this actually works. Oh, they will talk about this in the next lesson. Array decay solves a C-style array passing issue. Array decay solves both challenges we encountered at the top of the lesson. When passing a C-style array as an argument, the array decays into a pointer, and the pointer holding the address of the first element of the array is what gets passed to the function. So although it looks like we are passing the C-style array by value, we are actually passing it by address. This is how making a copy of a C-style array argument is avoided. C-style arrays are passed by address, even when it looks like they are passed by value. Now consider two different arrays of the same element type but different lengths. These are distinct type incompatible with each other. However, they will both decay into the same pointer. Their decayed version are interchangeable. Dropping the length information from the type allows us to pass arrays of different length without a type mismatch. Two C-style arrays with the same element type but different length will decay into the same pointer type. The following example will illustrate two things. That we can pass arrays of different length into a single function, that our function parameter receiving the array can be const pointer of the array elements type. So const int array, const int array. If this wasn't const, if the array wasn't const, would this work? Let's just check. So we have this, we have these two. If I run it normally, I get 21. Yeah, I get 2 and 1. I should just add this. If these are not const, then what would happen? Oh, this still works. I'm guessing what is passed into it becomes a constant then. Because the C-style array is passed by address, the function has direct access to the array passed in and can modify its element. For this reason, it's a good idea to make sure your function parameter is constant if your function does not intend to modify the array elements. One problem with declaring the function parameter as pointer integer array is that it's not obvious that array is supposed to be a pointer to an array of values rather than a pointer to a single integer. For this reason, when passing a C-style array, it's preferable to use an alternate declaration form, int array. So treat it the same as const int pointer. The program behaves identically to the prior one, as the compiler may interpret the function parameter as const int array, the same as const int pointer. However, this has the advantage of communicating to the caller of array to the caller that array is expected to be decayed C-style array, not pointed to a single value. The downside of using this syntax is that it makes it less obvious that array has decayed. So you will need to take extra care not to do anything that doesn't work as expected with the decayed array. Although array decay was a clever solution to ensure C-style arrays of different lengths could be passed to a function without making expensive copies, the loss of the array length information makes it easy for several types of mistakes to be made. First, size of it will return different values for arrays and decayed arrays. Size of prints 4, assuming a 32-bit address. Size of here will print 12 for 4-byte integers. This means using size of on a C-style array is potentially dangerous, as you have to ensure you are using it only when you access the actual array object, not a decayed array or a pointer. In the prior lesson, we mentioned that size of divided by size of pointer to array was historically used as a hack to get the size of C-style array. This hack is dangerous because if array is decayed, size of array will return the size of a pointer rather than the size of the array, producing the wrong array length as a result. Fortunately, C++'17's better replacement, std size, will fail to compile if passed a pointer value. So std size won't work on a pointer, and then over here it prints 3. Second, and perhaps most importantly, array decay can make refactoring difficult. Code that works as expected with a non-decayed array may not compile when the same code is using a decayed array. Third, not having length information creates several programmatic challenges. Without length information, it is difficult to sanity check the length of the array. Users can easily pass in arrays that are shorter than expected, which will then cause undefined behavior when they are subscripted with an invalid index. So how do we show array has at least 3 elements? Array 2. We can pass in a second argument. Now, having the array length also creates challenges when traversing the array. How do we know that when we have reached the end? There are solutions to these issues, but these solutions add both complexity and fragility to a program. Historically, programmers have worked around the lack of array length information via 2 methods. First, we can pass in both the array and array length as separate arguments. However, this still has a number of issues. The caller needs to make sure that the array and array length are paired. If the wrong value of the length is passed in, the function will still malfunction. There's a potential sign conversion issue if you're using std size or a function that returns a length as size t. Second, if there is an element value that is not semantically valid, we can instead mark the end of the array using an element of that value. That way, the length of the array can be calculated by counting how many elements exist between the start of the array and this terminating value. The array can also be traversed by iterating from the start until we hit a terminating element. The nice thing about this method is that it works even if the implicit function calls. But this method also has a number of issues. If the terminating element doesn't exist, traverser will walk right off the end of the array, causing undefined behavior. C-style array should be avoided in most cases because of the non-standard passing semantics and risk associated with decayed arrays losing their length information. C-style arrays have generally fallen out of favor. We recommend avoiding them as much as possible. So when a C-style array is used in modern C++, typically in two cases, to store constant expression global program data, because such arrays can be accessed directly from anywhere in the program, as parameters to functions or classes that want to handle non-expression C-style string arguments directly. These are two possible there are two possible reasons for this. First, converting a non-constant expression C-style string to a string view requires traversing the C-style string to determine its length. If the function in a performance critical section of the code If the function is in a performance critical section of the code and the length isn't needed, then avoiding the conversion may be useful. Second, if the function calls other functions that expect C-style string, converting to a string view just to convert back may be suboptimal. So what is array decay and why is it a problem? When a C-style array is evaluated in most contexts, it will be implicitly converted to a pointer to the array's element. Decayed arrays lose their length information, which makes it easier for length-related bugs to be introduced into the program. Why do C-style strings use a null terminator? When a C-style array is passed to a function, it decays and loses their information. If C-style string doesn't have a null terminator, the function would not be able to determine how long the string was. Extra credit. Why do C-style strings use a null terminator instead of requiring both a decayed C-style string and an explicit length information to be passed to a function? There are probably many answers to this question, but here are some. The ergonomics would be horrible, as we would have extra parameters and matching numbers everywhere. It would be very easy for the string and provided string length to not match properly. The string length is essentially an invariant of the string itself. Extra credit too, even if C++ wanted to implement having to pass explicit length information, why wouldn't it work? Passing both C-style string and explicit length information is only possible if a function is called explicitly. If a function is called implicitly, there is no way to pass along the length information. Consider a statement like std cout C string. Binary insertion operator can only take two operands. There is no way to pass another argument representing the length information. The null terminator approach doesn't have this issue. So pointer arithmetic and subscripting. In lesson 16.1, we mentioned that arrays are stored sequentially in memory. In this lesson, we will take a deeper look at how arrays indexing math work. Although we won't use indexing math in future lessons, the topics covered in this lesson will give you insight into how range-based for loops actually work. Will come in handy later when we cover iterators. Pointer arithmetic is a feature that allows us to apply certain integer arithmetic operators to a pointer to produce new memory addresses. Given some pointer plus 1 returns the address of the next object in memory. So if pointer is int is an integer pointer and int is 4 bytes, pointer plus 1 will return the memory address that is 4 bytes after pointer. Then pointer plus 2 return the memory address that is 8 bytes after pointer. Oh, I see. On the author's machine, this prints this, and this. So const int pointer. This holds the memory of x. and pointer here, pointer +1, pointer +2. Now that each memory address is 4 bytes greater than the previous. Although less common, pointer arithmetics also works with subtraction. So this will give the previous object. So 7, 8. And then we have 7C. No, wait. 8, 0. And then 4 bytes backwards, we get 7C. And then 4 bytes backwards, we get 7, 8. Applying the increment and decrement operators to a pointer do the same thing as the pointer addition and pointer subtraction. So int math. Okay. Subscripting is implemented via pointer arithmetic. In the prior lesson, we noted that the subscript operator can be applied to a pointer. Let's take a deeper look at what's happening here. It turns out the subscript operator print pointer n is a concise syntax equivalent to a more verbose expression. The pointer plus n and then dereference that. Wait, I don't understand this. You will note that this is just pointer arithmetic with just some additional parentheses to ensure things evaluate in the correct order, and implicit dereference to get an object at that address. First, we initialize pointer with array. When array is used as an initializer, it decays into a pointer holding the address to element with index 0. So pointer now holds the address of element 0. Next, we print pointer 2. Pointer 2 is equivalent to pointer plus 2, which is equivalent to pointer plus 2. Pointer plus 2 returns the address of the object, that is 2 objects past the pointer, which is the element with index 2. The object at the index address is then returned to the caller. Oh, this is the reference. I forgot. So let's use subscripting to get the address and the values of our array elements. So std the address of array 0, address of 1, address of 2, 3, 2, 1. Now let's do the equivalent using pointer arithmetic. So array plus 1, array plus 2, and then we are dereferencing it here. 3, 2, and 1. When first learning about array subscripting, it's natural to assume that the index represents a fixed element within the array. Index 0 is always the first element. Index 1 is always the second element. This is an illusion. Array indices actually have relative position. The indices just appear fixed because they almost always index from the start. Remember, given some pointer, both pointer plus 1 and pointer 1 return the next object in memory. Next is a relative term, not an absolute one. Thus, if pointer is pointing to element 0, then pointer plus 1 and pointer 1 will return element 1. But if pointer is pointing at element 3 instead, then both pointer 1 will return element 4. So const int array and then pointer to array. So point 0 is like pointing at the first element, which is 9. This will produce 9, this will produce 9, so prints 9, 9. And then over here, this will produce 8, 8. Now set the pointer to point at element 3. So address of array 3. Now that we are pointing at element 3. So these two will print 6, 6, and then these two will print 5, 5. So 6 and 5. So 0, 1, 2, 3, 6. And then the next one is 5. However, you also note that our program is a lot more confusing if you can't assume that pointer 1 is always the element with index 1. For this reason, we recommend only using subscripting only when indexing from the start of the array. In the last lesson, we mentioned that the index of a C-style array can either be unsigned integer or signed integer. This wasn't done just for convenience. It's possible. It's actually possible to index a C-style array with negative subscript. It sounds funny, but it makes sense. Okay, so it's pointing at 6, and then negative 1 will point at 7. If we are at the start, and if we do negative 1, I'm guessing it causes undefined behavior. One of the most common uses of pointer arithmetic is to iterate through a C-style array without explicit indexing. The following example illustrates how this is done. So constant expression integer array 97531, constant integer begin array, and then n array plus size of array, and then for begin is not equal to n, begin plus plus. Yeah, I get it. In the prior lesson, we mentioned that array decay makes refactoring functions difficult because certain things work with non-decayed arrays but not with decayed arrays. One neat thing about this traversing an array this way is that we can refactor the loop part of the above example into a separate function exactly as written, and it still works. Okay. Range-based for loops over C-style arrays are implemented using pointer arithmetic. Consider the following range-based for loops. So constant expression integer array, for auto E array. Okay. If you look at the documentation for range-based for loops, you will see they typically implemented something like this. So auto begin minus expression, auto n minus x. What is this? This expression over here. So as long as begin is not equal to end, we keep incrementing it. So range declaration, then loop statement. Let's replace the range-based for loops in the prior example with this implementation. So array plus std size array. Note how similar this is to the example we wrote in the prior section. The only difference is that we are assigning begin to E and using E rather than just using begin directly. So why is array 0 the same as pointer array? Array 0 is a shorthand for array plus 0 and then dereferencing that. Okay. So C style strings. I'll just open the next chapter. In lesson 17.7, we introduced C-style arrays, which allows us to define a sequential collection of elements. In lesson 5.2, we define a string as a collection of sequential characters and introduced C-style string literals. We also noted that C-style string literal hello world has type const char14. If you hadn't connected the dots before, it should be obvious now that C-style strings are just C-style arrays with element type char or const char. Although C-style string literals are fine to use in our code, C-style string objects have fallen out of favor in modern C++ because they're hard to use and dangerous. Regardless, you may still run across uses of C-style string objects in older code, and we would remiss not to cover them at all. So defining C-style string. To define a C-style string variable, simply declare a C-style array variable of char or constant char, constant expression char. So char, const char, constant expression char. Remember that we need an extra character for the implicit null terminator. When defining C-style string within initializer, we highly recommend omitting the array length and letting the compiler calculate the length. That way, if the initializer changes in the future, you won't have to remember to update the length, and there is no risk in forgetting to include an extra element to hold the null terminator. In lesson 17.8, we discussed how C-style arrays will decay into pointer in most circumstances. Because C-style strings are C-style arrays, they will decay into const char pointer. This loss of information is the reason C-style strings have a null terminator. The length of a string can be regenerated by counting the number of elements between the start of the string and null terminator. When outputting a C-style string, cout outputs characters until it encounters a null terminator. This null terminator marks the end of the string so that decayed strings can be printed. If you try to print a string that does not have null terminator, this result will be undefined behavior. Consider the case where we are asking the user to roll a die as many times as they wish and enter the number rolled without spaces. How many characters will the user enter? We have no idea. Because C-style strings are fixed size arrays, the solution is to declare an array larger than we ever likely need. So 255. Prior to C++20, stdcin roles would extract as many characters as possible to roles. Nothing is stopping the user from entering more than 254 characters. And if that happens, the user's input will overflow the roles array and undefined behavior will result. Array overflow or buffer overflow is a computer security issue that occurs when more data is copied into storage than storage can handle. In such cases, the memory just beyond storage will be overwritten, leading to undefined behavior. In C++20, this operator was changed so that it only works for inputting non-decayed C-style strings. This allows operator to extract only as many characters as the C-style string's length will allow, preventing overflow. But this also means you can no longer use this operator to input to decayed C-style strings. We recommend the recommended way of reading C-style strings using stdcin is as follows. So cin get line roles, std size roles. This call to cin get line will read up to 254 characters into roles. Any excess characters will be discarded. Because getLine takes a length, we can provide the maximum number of characters to accept. With a non-decayed array, this is easy. We can use size to get the array length. With a decayed array, we have to determine the length in some other way. And if we provide the wrong length, our program may malfunction or have security issues. In modern C++, when storing inputted text from the user, it's safer to use std string as std string. Will automatically hold as many characters as needed. Will adjust automatically to hold as many characters as needed. One important thing to note is that C-style strings follow the same rules as C-style arrays. This means you can't initialize the string upon creation, but this means you can initialize the string upon creation, but you cannot assign values to it using the assignment operator after that. This makes using C-style strings a bit awkward. Since C style strings are arrays, you can use the subscript operator to change individual characters in the string. So string 1p. Oh, I see. Because C style strings are C style arrays, you can use std size to get the length of the string as an array. There are two caveats here. This doesn't work on decayed strings. It returns the actual length of C style array, not the length of the string. So character string 255, 6 characters plus null terminated. Std cout length. This prints 255. An alternate solution is to use string length function, which lives in the C string header. String length will work on decayed arrays and return the length of a string being held, excluding the null terminator. String length. Okay, I see. However, string length is slow as it traverses through the whole array, counting characters until it hits the null terminator. Other C-style string manipulating functions. Here are a few useful ones. String length returns the length. String copy overwrites one C-style string with another. String concatenate appends one C-style string to an end of the other. C compare compares two C-style string, returns 0 if equal. Except for string length, we generally recommend avoiding these. Avoid non-constant C-style string objects. Unless you have a specific compelling reason to use non-constant C-style strings, they're best avoided as they're awkward to work with and are prone to overruns, which will cause undefined behavior. In the rare case that you do need to work with C-style strings or fixed buffer sizes, we recommend using the well-tested third-party fixed length size string library designed for that purpose. Okay, what's this? Write a function to print a C-style string character by character. Use a pointer and pointer arithmetic to step through each character of a string and print that character. Write a main function that tests the function with the string literal hello world. Okay, so I will do void print characters hello world. This has to be char. If this array actually while the element is not a null terminate is not a terminator, so while this std cout print the element of the array and then new line and then array like that. Let's see. Okay, hello world. It printed. Use a pointer and pointer arithmetic. Okay, they did what I did. Uh, and also it's better to do this. Repeat quiz 1, but this time the function should print the string backwards. Okay, let's see. Wait, if this is a constant, then how am I able to increment it? I think the values in the arrays I cannot change, but the pointer I can. Anyways, new. Uh, I will have this as const char pointer 2, and then this will be pointer 1. Then remove this. Pointer 1. And then pointer 2 is equal to pointer 1. Actually, hold on. I will do this. And then I will do int counter is equal to 0. While counter does this make sense? So you're getting an array. This is counting the length. And now while counter is more than 0, we don't need a second pointer actually. Std cout. Did they say to use a pointer arithmetic for the second one as well? So it starts with 0. You keep incrementing until you hit the length of the array. And now you keep decrementing and keep printing as you're decrementing. So this is O of n. This is also O of n. But it's going O of n twice. Yeah, so it printed the dominating character though, I think. Hold on. Yeah, it did print the dominating character. So I should do one more minus minus. So how did they do it? They did the same thing, but they used pointer arithmetic. So, right. Or this is what I wanted to do with pointer too. Like how what they're doing with pointer. C style string symbolic constants. And then the next lesson is multidimensional arrays. Yeah, it works perfectly. In the previous lesson, we discussed how to create and initialize C style string objects. Okay. While the above two methods produce the same result, C++ deals with memory allocation for these differently. Const char and then const char pointer. In case 1, Alex is pointed into read-only memory somewhere. Then the program allocates memory for a C-style array of length 5. 4 explicit characters plus a null terminator, and initializes that memory with the string Alex. So we end up with 2 copies of Alex. One in the global memory somewhere and the other one owned by name. Since name is constant, making a copy is inefficient. In case 2, how the compiler handles this implementation defined. What usually happens is that the compiler places the string orange into a read-only memory somewhere and then initializes the pointer with the address of the string. For optimization purposes, multiple string literals may be consolidated into a single value. For example, these are two different string literals with the same value. Because these literals are constant, the compiler may opt to save memory by compiling these into a single shared string literal with both name1 and name2 pointed at the same address. Type deduction with constant C style string. Type deduction using C style string literal is fairly straightforward. So, character pointer, also character pointer, and then const character reference 5. You may have noticed something interesting about the way stdcout handles pointers of different types. Consider the following example. So an array, so integer array, character array, and then pointer. On author's machine, this printed. So an array, and then when if an array of integers don't have a null terminator, how does cout know when to terminate? Why did this integer array print an address? But character arrays print a string? The answer is that the output streams stdcout make some assumptions about your intent. If you pass a non-character pointer, it will simply print the contents of that pointer. However, if you pass an object of type character pointer, it will assume you're intending to print a string. Consequently, instead of printing the pointer's value, it will print the string beyond the it will print the string being pointed to instead. While this is designed most of the time, it can lead to unexpected results. Consider the following case. So character C, and then we have reference to C. The program is intending to print the address of variable C. However, reference address of C has type character pointer. So stdcr tries to print this as a string, and because C is not null terminated, we get undefined behavior. In the author's machine, we get this. Why did it do this? Well, first it assumed this address of C was a C style string. So it printed Q. Hold on. Shouldn't it print the address of C? No. If it has the address, it prints the contents. Yeah. For characters. For characters, if it has the address of the character, then it prints the content. Next in memory was a bunch of garbage. Eventually, it ran into some memory holding a zero value, which it interpreted as a null terminator, so it stopped. What you see may be different depending on what's in memory after variable C. This case is somewhat unlikely to occur in real life, but it illustrates how things work under the hood and how programs can inadvertently go off the rails. If you actually want to print the address of a character pointer, static cast it to type const void pointer. So const void. Oh, so it's pretend. So it's like pointing to a void. Payable string view for C-style string symbolic constants. A multi-dimensional array. Consider a game like tic-tac-toe. The standard board for this game is a 3x3 grid with players taking turns placing X and O symbols. The first to get 3 symbols in a row wins. While you could store the board data as 9 individual variables, we know that when you have multiple instances of an element, it's better to use an array. A C-style array of integer. So value 0 is empty, 1 is player 1, 2 is player 2. This defines a C-style array with 9 elements arranged sequentially in memory. You can imagine these elements laid out in a single row of values like this. The dimension of an array is the number of indices needed to select an element. An array containing only a single dimension is called a single dimensional array or one dimensional array. In the previous lesson, we noted that elements of an array can be of any object type. This means element type of an array can be another array. Defining such an array is simple. So int array 35. An array of array is called a two-dimensional array because it has two subscripts. With a two-dimensional array, it is convenient to think of the first subscript as selecting the row and the second subscript as selecting the column. Okay, so row 0, row 0, row 0. So within row 0, there's this array which is being subscripted with 0, 1, 2, 3, 4. To access elements of a two-dimensional array, we simply use two subscripts. C++ even supports multi-dimensional arrays with more than 2 dimensions. Memory is linear, so multi-dimensional arrays are actually stored as a sequential list of elements. There are two possible ways for following array to be stored in memory. C++ uses row major order, where elements are sequentially placed in memory row by row, ordered from left to right, top to bottom. Okay, to initialize a two-dimensional array, it's easier to use nested braces with each set of numbers representing a row. Row 0, row 1, row 2. When using inner braces, missing initializers will be value initialized. So 1 2 0 0 0, then 6 7 8 0 0. In such cases, the compiler can do the math to figure out what the leftmost length is. Okay. An uninitialized multidimensional array can omit only the leftmost length specification. So we can omit this, and using the initializer, the compiler will reduce the length. With one-dimensional array, we can use a single loop to iterate through all of the elements in the array. So array 1, 2, 3, 4, 5. Wait, this is one-dimensional. With two-dimensional arrays, we can do this. Size t, rows 0. Oh, size t first it's 0. And then it increments. And over here, the same thing for the column. Cartesian coordinates versus array indices. In geometry, the Cartesian coordinate system is often used to describe the position of objects. In two dimensions, we have the coordinate axis, conventionally named x and y. The Cartesian position of an object can be described as an xy pair, where x coordinate and y coordinate are values indicating how far to the right of the x and how far above the y axis an object is positioned. Sometimes the y-axis is flipped. Now let's take a look at a 2D array layout in C++. This is also a two-dimensional coordinate system where the position of an element can be described as row column. Okay. Multi-dimensional STD array. In the prior lesson, we discussed C-style multidimensional array. We generally want to avoid C-style arrays. There is no standard library for multidimensional array class. Note that CSTD array is implemented as a single dimensional array. So the first question you should ask, is there a standard library class for multidimensional array? The answer is no. The canonical way to create a two-dimensional array of STD arrays to create STD array where the template type argument is another array. Array and then another array of int 4. There are a number of interesting things to note about this. When initializing a multidimensional STD array, we need to use double braces. The syntax is verbose and hard to read because of the way templates get nested. The array dimensions are switched. We want an array with 3 rows of 4 elements. So array 3 is natural. STD array of 4 elements. 4 elements. And we have an array of 4 elements with 3 length. Okay. So in C style we mention 3 first and then 4, but over here we're mentioning 4 first and then 3. You can also pass a two-dimensional STD array to a function just like one-dimensional STD array. Okay. Making two-dimensional STD array easier using an alias template. In lesson 10.7, we introduced type aliases and noted that one of the uses of type aliases is to make complex types simpler to use. So array 2D integer 3, 4. This allows us to use array 2D in 3, 4 wherever we want to use 3 times 4 two-dimensional STD array. So this is a perfect place to use alias template. So array 2D array 2D, std, array t, column and row, size t, and then array 2D over here. Notice how much concise and easy to use this is. Getting the dimensional length of a two-dimensional array. With one-dimensional array, we can use the size member function to get the length of the array. But what do we do when we have a two-dimensional std array? In this case, size will only return the length of the first dimension. One seemingly appealing but potentially dangerous option is to get an element of the desired dimension and then call size on that. So we have rows. Array.size will give 3, and then the inner array dot size we have to access one of the elements. The above code is flawed as it will produce undefined result if any dimension other than the last has the length of 0. A better option is to use a function template to return the length of the dimension directly from the associated non-time template parameter. So row length, return row, and then return column. This avoids any undefined behavior if the length of any dimension is 0, as it uses the type information of the array. Arrays with 2 or more dimensions have some challenges. They are more robust to define and work with. It's awkward to get the length of the dimensions greater than the first. They're increasingly hard to iterate over. One approach is to make a multi-dimensional array easy to work with is to flatten them. Flattening an array is the process of reducing the dimensionality of an array. For example, instead of creating a two-dimensional array with rows and columns, we can create a one-dimensional array with row time column elements. This gives us the same amount of storage using a single dimension. However, because our one-dimensional array only has a single dimension, we cannot work with it as a multi-dimensional array. To use this, we can provide an interface that mimics a multi-dimensional array. This interface will accept two-dimensional coordinates and then map them to a unique position in the one-dimensional array. Here's an example of that approach that works in C++11 or newer. So, yeah, this is getting confusing. They're defining an array over here. Array flat 2D int array. So rows. So the 3 rows and 4 columns. They're defining array flat 2D. So using array flat 2D. Okay, class array view. Array flat 2D is std array rows times column. And then array view 2D is an array view. And then array view 2D reference wrapper. And then they're mentioning their own operators. Because this is getting confusing. I can understand what they're doing, but it's very verbose. Array view row column, or they're accessing using both row and column like this. In C++23, subscripting operator was extended to accept multiple subscripts, so you can overload it to handle both single and multiple subscripts. std mdspan introduced in C++23. std mdspan is a modifiable view that provides a multi-dimensional array interface for a contiguous sequence of elements. By modifiable view, we mean that std mdspan is not just a read-only view if the underlying sequence of element is non-constant. The following example prints the same output as a prior example but uses mdspan instead of our custom view. So mdspan mdview array.data. mdspan, let us define a view with as many dimensions as we want. First parameter to the constructor of mdspan should be a pointer to the array data. This can be a decade C style array, or we can use data member function of array or std vector to get this data. To index a mdspan in one dimension, we must fetch the pointer to an array data, which can then use data handle member function. We can then subscript that. In C++, this operator accepts multiple indices, so we use row, comma, column as our index. mdview row, comma, column. The data handle member gives us a pointer to a sequence of elements which we can then index. Print array dimension. mdspan calls these extents. So extents, extent 0, extents, extent 1. Oh, so mdview.extends, it returns the array of dimensions, right? Chapter 17, Siberian Quiz. Okay, I will just read this and then I will end the stream. Fixed size arrays require that the length of the array be known at the point of instantiation and that the length cannot be changed afterwards. C-style arrays and std arrays are both fixed size arrays. To get the length of a array, std array, we can ask std array object for its length using the size member function. In C++ 17, we can use std size non-member function. In C++ 20, we can use ssize, which returns the length as a large signed integral type. Use of the subscript operator, no bounds checking, is done in this case. Use the add member function that does subscripting with runtime bounds checking. Use std get function template, which takes the index as a non-type template argument and does compile time bound checking. You can pass std array with different element types and lengths of a function using function template with a template parameter. Aggregates in C++ support a concept called brace elision, which lays out some rules for when multiple braces may be omitted. Generally, you want to omit braces when initializing a std array with scalar single values. You cannot have array of references, but you can have an array of reference wrapper which behaves like a modified value reference. The stdref and cref functions were provided as shortcuts to create reference wrapper and constant reference wrapper. Use static assert whenever possible to ensure std array using ctad has the correct number of initializers. Okay, pointer arithmetic. What's wrong with each of these snippets? How would you fix it? So std array count 0. Count is less than or equal to the size of array. So it shouldn't be equal to. It should just be less than. The conditional in the for loop uses, yeah. So B, what is the error here? Print array. First, it should be constant. Yeah, this should be constant. I think that's the only part. Array decays to a pointer when it is passed to print array. Range-based for loops can't work with pointer to an array because the size of the array isn't known. Oh, I see. Use std array instead, which doesn't decay. So over here, enter the test scores is length, C in length. Oh, I think this has to be. Does this need to be compile time constant? I can't remember. Length is not a constant expression, cannot be used to define the length of std array. Use std vector instead. In this quiz, we are going to implement Roscoe's Potion Emporium, finest potion shop in the land. This is going to be a bigger challenge. Implement a program that outputs the following. And this is so much. The player starts with a randomized amount of gold between 80 and 120. Sounds fun, let's do it. Because this is hard to implement all at once, we'll develop this in step. Okay. Create a potion namespace containing an enum named type containing the potion types. Create two std arrays and int array to hold the potion's cost and string view array to hold the potion's name. Also write a function named shop that enumerates through the list of potion and prints their numbers and names and costs. The program should output the following. Okay, whoops. So namespace potion containing an enum named type. Potion enum type. And then I don't know why it keeps doing this. I'm using Alt Tab. Enum named type containing potion types to hold the potion names. What are the names of all the potions? Healing, mana, speed, invisibility. Healing, mana, speed, invisibility, and then max potions. Max potion types. Also write a function named shop. Should shop be inside potions? That enumerates through a list of potions and prints their numbers and names and cost. Std array of int. Const int std array 20, 30, 12, 50. 20, 30, 12, 50. And then const. No, wait, this is wrong. Std string view. include string, include array. Healing, mana, speed, invisibility, cons, string view, cost, and then name. Names cost. So the function shop that enumerates through the list of portion and prints there. Void shop. For const auto reference C cost. Oh no, let's do int I is equal to 0. I is less than max portion types, and then plus plus I. std cout. So we have how do we hold on. Here is our selection for today. Heating cost 20. I think like this. I names I. Cost. Is this what they're expecting? Portions. Portion shop. std string view. I don't get what the issue is. Cannot convert initializer list to std string view. Using std string. Was it like this? I can't remember how you use this. Let's see what they did. Const expression. Oh, oops. Yeah, this is a mistake. Std array. String view. Isn't there a way to loop through the enum? Do field. Oh yeah, we cannot do this. Max portion types. Argument conversion from int. Signed, unsigned mismatch. Static cast. Const expression. Portion size. Static cast. Max portion type. What's the? Is it assigned? Unsigned portion size. Let's do portion now. No, wait, they're using max portion here. Hold on. What is the issue? I can do this, but I don't know what the issue is. Let's see. 13 missing specified type int assumed. What do they mean missing specified type? std array. Wait, string view. Argument conversion. The following warning is treated as an error. Argument. So it's in line 18. Should I do this unsigned integer? No, std size. Size d. So healing cost 20, mana cost 30, speed cost 12, and invisibility cost 50. Auto potion speed types. And I should use these static asserts. Here. Names and then cost. Create a player class to store the player's name, potion inventory, and gold. Add the introductory and goodbye text for Roscoe is a Porium. Get the player's name and randomize their gold. The program should output the following. Okay, so first of all, let's do the first line std cout /n. I should put this namespace portion in the header file. Add a new item. Portions.header. Portion.header. Add. And then I will create another. 5 for the player. So namespace. Include portion.h. And then I will also what's this? Okay, I'll just switch this to player.h. Player underscore h. Should I put header guard for the portion one also? Class player. Create a player class to store the player's name, portion, inventory, and gold. Add the introductory and goodbye text for Roscoe's Emporium. Get the player's name and randomize their gold. Player. So how do you do the constructor again? Public. Player. STD string name. Include string private name std string name and integer health. Portion, inventory, and gold. No integer. Can you have negative gold? I'll just do this on side. Player name. And then the gold should be randomized, right? Get the player's name and randomize the gold. Is it this? Dot name. I cannot remember how. I'm forgetting a lot. Input name. I'll have to look at the answers because I remember absolutely nothing. And what is this player? Isn't this how we do constructors? Let's see. I have to look at the answer. So portion, then player, minimum starting goal, max starting goal. Did they say it has to be between 80 and 120? String M name. Oh yeah, it should be M underscore name gold. So M inventory integer portion max portion. Okay. This is what they meant by inventory. And I need to include the header card in the portions library. Portion underscore H. And if I forgot what the explicit keyword does. And then the gold and inventory, we return it. These are the getter functions. Okay, I can imagine that. But the constructor is done like this. String view. I forgot so much. So let's see. So then we initialize the player. It says error constant here. So we have std array. Why does it say error constant? Max portion types. Let's see. So shop. Then welcome to this and then enter your name. Std string. I completely forgot everything. And then player name player. Okay, I will have to go somewhere. But just let me wait. First we initialize the player. Also there's an exit. So if I run this, let's see if I get any errors. Player.age 21 16. Random is not a class or namespace name. Did I import it correctly? It's random.h. Wait. Random.h. Why doesn't this work? Didn't they define random.h on their own? Where is this? Wait. Maybe it's capital R. Okay, random is defined. Or let's just forget random. Let's just initialize it with a random value. Gold. Let's do starting gold 120, and then conversion from constant. Wait, hold on. Play.h 21. I think initializing like this allows Naren conversion, right? So that's why there wasn't a warning here. Oh, now it works. Bob. Okay. Thanks for shopping at. Hello, Bob. You have 120 gold. Okay, I will end the stream here. And then next stream, I might continue with either math or the next topic, whatever that is. Okay, then. See you next time, I guess.